Thank you very much. And thank you all for sticking until the last session of the workshop. So I'm going to talk about some recent work that I did with my student, David, from NYU. And so, yeah, because it's the last, almost the last lecture, I'll try to keep it a bit informal. First, so that the topic of, so this title might seem a little bit cryptic, for maybe if you're not familiar with what it says. The talk is about reinforcement learning. Right, so reinforcement learning, probably you have seen it in the news and in the Twitter. If you're following, machine learning on Twitter, it's full of extraordinary results, like very flashy results of things that we can do with this methodology. In a sense, it's not a new technology, right? That these are these are results that already were kind of appearing in the 90s. With these algorithms, we know how to play backgammon, and now the video games become more and more, let's say, fancy. Go, video games. Let's see if this thing plays. Okay, so this is the sort of things that the kind of algorithm, the kind of tasks that we know how to do with reinforcement learning. So basically, we can teach a little humanoid how to run under very simplified physics. We can do also learn how to do hide and seek, by training these little agents on the grid. And more recently, I don't know if you saw, there were like two very splash things, right? The first is this ability of this robotic hand to solve the Rubik cube, right? I mean, here what is impressive is the control, right? Is the fact that we can actually the way that the physical control, the dexterity was completely solved by reinforcement learning. And actually, even more recently, yesterday, if you saw, there was this Nature paper on a DeepMind algorithms being able to reach a grandmaster level status on StarCraft, which is I'm not a video game player myself, but apparently this is actually known to be a serious video game that is not so easy to solve, right? So these are all interesting, and actually beyond games, actually it's even spreading into areas of physical science. So this is a very nice recent paper where now people are trying to use reinforcement learning techniques to solve retrosynthesis for molecules. So basically, I want to synthesize a molecule in the lab. What is the chemical reaction I should follow to get to optimize for a certain objective function? We are starting to also to use this for quantum control, and even for things that might look a bit crazy, like integer programming, right? So replacing the cutting plane method by maybe different heuristics, right? So all these abilities, in a sense, they might sound a bit remarkable, surprising, right? How come this algorithm is able to do it? In particular, when we have observations that are, again, in the higher dimensional regime, right? So many of these algorithms, the only thing that they have access to are the pixels, right? The raw pixels. And so these are all very nice things, but at the same time, we already identify in the field that there's a lot of things that we are not where we would like to be, in the sense that all these successes, they come at the expense of having to interact with the environment a massive number of times, many orders of magnitude more than a human would require to get to reach a similar level of performance. And not only we are in the regime where we are still using the environment in a poor manner, we also, in the theoretical side, we have very little guarantees, right? And I think one of the topics of this workshop is learning with guarantees, right? And how can we certify that things are going to go well? Well, this is a territory where still, there's still a lot of things to do. So just to give you the setup, the mathematical setup that we are going to be using today. So the natural, the simplest framework that people use to study this problem is what's called a Markov decision process, right? And probably you have seen this diagram many times, right? Where you have, so there are two components. There's an agent, and there's an environment, and it's all about online decision making, right? So the goal of the agent is to try to learn how to interact with the environment. So how is the interaction about? So the agent observes certain state and observes certain reward from the world, and then from this information, he decides to make a new action, right? And so what are the ingredients of the game? The ingredients of this object, this Markov decision process, contains a set of states. So this could be the different states in which you might be in a game of Go, could be all the possible configurations of the board, for example. the actions would be at every step in time, what are the things that the agent is able to do? What are the choices that I can make? And then the dynamics are modeled with a Markov. I mean, this is like where they have this assumption, right? The dynamics are modeled with a Markov transition kernel that might, of course, be might be deterministic or might be stochastic. And then we are giving we are placing the agent in some initial state. And as I said, at every time I have make an action, the environment is going to give me some reward back. And so the goal of the game, like a bit more mathematically precise, is to find a policy. So what is a policy? Is a mapping from state to action. So given the state I'm in, I want to make a decision, a very good decision of what I want to do in this environment. Right? So I look at the board of the game of Go. Where should I put my next stone? Right? So you want to have a policy, and the policy needs to maximize the expected sum of discounted rewards, right? So of course this is by no means the only setup where you can do, but it's the simplest mathematically. I'm just going to stick with the discounted thing, right? Like basically the rewards that matter the most are the ones that are immediately ahead of me, right? And this gamma, think of it as a kind of a discount factor that goes to 0. Okay, so this is the setup, and so let's see if that works. Okay, so what are the key challenges? The reasons why this problem is hard, right? And in a sense, and why should it be interesting for us, right? So the first interesting challenge is that probably you also have seen this many times in the literature, is that there's this fundamental tension between exploration and exploitation, right? So if I'm in an environment and I want to maximize the sum of the expected rewards, I need to go out there and to be able to figure out, to try to get information from maybe like high reward states that are out there that I haven't seen before. So I have an incentive to go out there and explore. But at the same time, I also have an incentive to continue to exploit strategies that are currently known to be true, right? And this kind of tension is completely captured in these. For example, I mean, if you think in terms of the classical statistic literature, like bandits is really all about trying to understand the nature of this trade-off. But in reinforcement learning, we not only have this trade-off, but we also have what's called this credit assignment problem, right? I mean, the example that I typically hear is that, okay, why should you spend so much time and effort, like money in the US to study at the university, right? This seems like a big word. I mean, of course, at some point, right, this might be a payoff, right? And in a sense, like figuring out that there's some actions that you are doing at this time that might be useful to collect future rewards. That is as you can see, it introduces a very complicated like variance blow up, right? I mean, the number of uncertainty that you need to accumulate through time might potentially blow up. And then the last one, of course, is that in many problems that we care about, the state representation is not given to us in a way that can be processed and understood very well, right? I mean, like an agent, a reinforcement learning agent, should be able to operate with cameras, right? With things that have this huge complexity of the world, that the information is not given to us in a nice processed way, right? We need to figure out how to extract these useful representations from there. So you see, it's like this huge, it's like 3 levels of difficulty that are, again, one on top of each other that you might not find in the traditional, let's say, supervised learning setup. And so what are the kind of the 3, let's say, if you had to organize the paradigms, like the strategies, like the kind of the way to think about this problem that exists. So there are essentially like 3 different flavors of that. One is something that people call model-based. Maybe the name of model-based is not very appropriate, as you will see later. But this idea really has this, it's something that maybe it's closer to the people on control theory, right? So if I want to basically get a good policy, it means that I need to be able to solve a control problem, except that the system that I'm trying to control, I don't know it. So a natural strategy is to say, well, maybe first I will estimate the system, right? Estimate the dynamics, and once I know the dynamics, I can solve the optimal control problem on the basis of these maybe potentially wrong dynamics, right? As you can see, these might enter this like instability, right? If you have a small error of modeling error, you might be controlling the wrong system, right? So that's an area where typically we have, there are some interesting like fundamental problems to solve. The other framework is that the one that we are essentially be focusing on today is based on this idea, but like basically the power of dynamic programming, right? This is the idea that I can characterize the optimal policy, the optimal way to behave in the world. There's a very natural recursive structure, right? So if I know how to optimally go from state 1 to state n, In particular, this characterizes the optimal policy to go from any neighboring state to the end, right? This is the natural structure of dynamic programming. So this is actually, if you might have heard about this Q-learning algorithm. Like Q-learning is basically an algorithm that really leverages the recursive structure of the value of the optimal policies that we have in Markov decision processes. And the way this is actually computed, so a very important object that we will be studying is what's called a value function, right? So the value function is basically a mapping that sends to any state in my world what is the expected reward I will collect if I had to run my policy starting from that state, right? And as you can expect, this value function, right, as you will see later, satisfies a very important recurrence equation that is called the Bellman equation. We'll see it later in a second, right? But in a sense, these kind of approximate dynamic programming algorithms, what they try to do is that they try to leverage the recursive structure, like the geometry of the MDP, through these kind of equations. And lastly, this thing works. Yes, and the other paradigm, the other framework that is also very popular is what's called like a policy gradient, right? The policy gradient is essentially going back to the original setup, right? And I just see this as a loss function with respect to the policy, and I forget about the dynamics, I forget about the recursive structure of the world, and I just directly try to find a policy that will give me the maximum rewards, like the maximum expected rewards. And these, I mean, one can actually see that essentially this is a derivative-free method, right? This is not using any kind of different regularity structure of the environment, right? And surprisingly, or not surprisingly, this thing is efficient in some environments, but there's some questions as to, what are basically the properties that make this algorithm competitive with these other ones. Sure.
Maybe just a comment. Why is this method called policy gradient?
Yes, it's a good question. It's because formally you parameterize the policies with some parameter, and you use what's called a policy gradient theorem that essentially builds an estimator of the gradient, an unbiased estimator of the gradient by sampling, right? It's like this expectation. So it's called policy gradient because it's pretending to estimate the gradient, but the algorithm is a gradient-free method, right? Yeah. Sorry? You estimate the gradient, but the same way that if you have only access to the function, right? You can estimate the gradient of the function by just evaluating the function at the cloud of points, right? The estimation of the gradient is going to be very bad in general, right? It's like if I have an oracle that cannot compute the gradient of the function, I can estimate the gradient of the function by just basically evaluating the function at different points, right? So that's the Anyway, we're not going to talk about policy gradients, so hopefully this is not going to be a big deal for us today. Okay, so in our reinforcement learning, of course, we also have this course of dimensionality, right? In the sense that if I want to understand, for example, how to do well on a problem on a game like Go, right? The state space soon becomes incredibly large, right? So you can imagine that if I don't make any kind of assumption, if I treat the problem in all its discreteness, it's really that the complexity at least is going to depend on this product, right? So in other words, if I don't make if I don't leverage any structure in the world, things are going to, of course, necessarily go bad when this thing explodes, right? And so the way we typically leverage this structure is through what we call the function approximation, right? So instead of actually trying to estimate these value functions or these structures, have one different estimation that is dependent for every state, we use what's called a parameterization, right? That in that case is going to be typically differentiable, that tries to treat this value function through some kind of low-dimensional structure, at least some structure that incorporates some information. So in particular, the deep reinforcement learning, what they consider is they consider this mapping to be implemented with a neural network. Okay, so in a sense, the question, the pitch of this talk is once we introduce this step that is necessary if we want to basically avoid the course of dimensionality, how can we use this function approximation yet have some kind of guarantees that what we learn is going to be consistent? So today we are going to really, as I said, we are going to focus on the value estimation, on the one particular step of this approximate dynamic programming algorithm. So this is actually what's called the temporal difference learning. And we are going to see that there's an interesting interplay between the geometry of the Markov decision process and the geometry of your function of your class of functions that you approximate. Right? Basically, the geometry of the neural network is going to interact with the geometry of the environment. And we'll see that we are going to basically recover some cute properties that are also, if you are familiar with the deep learning literature, these properties of neural networks that involve like homogeneity or the fact that you have this kind of residual architecture. Here they appear again, right? We see that these things turn out to be very interesting properties. Okay. So let's now focus a little bit on the approximate dynamic programming, the dynamic programming aspect of this problem. So this is going to be our central object. Okay. So we are not even going to try to learn the policy. The thing that we are going to only try to do today is to estimate the value of a policy, right? So you have a policy, and you want to estimate what is the expected value, the expected reward that this policy will collect if I start at any point in state. Okay. So as I said, this is a key step within the approximate dynamic programming learning. So what is the recurrence that this value function satisfies? So this you can obviously see that the fact that I have this kind of like a exponential thing, I can just take one exponent. I can isolate the first term, and then I can use the other term in the exponent. So basically, this is just trying to take the first term here, and then gamma times the rest term. This you get exactly the same object. So the fact that the optimal value function satisfies this linear equation that is called the Bellman equation. Okay, and this is actually something that we can establish very well in the case where you have discounted rewards. In the other cases where you have no discounts, you can derive similar things, but you need to do a little bit more work. But let's just stick with the discounted reward case.
And your actions are deterministic?
Here, the policy I'm assuming that is, I don't even need to assume that it's deterministic, but here, yeah, for the purposes, because my policy is fixed, it doesn't really change anything in my development, right?
But it's deterministic.
Here.
Up there, you say AK is equal to Q.
Oh yeah. So here it's true. So I could just put a sample here, and it would be drawn by this expectation anyway. Okay. Okay. So how can we estimate this value function using this, trying to leverage this recurrence? So the most popular algorithm to try to leverage this recurrence is called the temporal difference learning, the TD learning, right? So what is the TD learning trying to do? Intuitively, what I'm looking for is a fixed point, right? It satisfies this equation. So what I'll try to do is I look at my current estimate, and I'll try to update my estimate such that I try to basically I correct it by the gap in this equation, right? Basically, and that's a very natural algorithm. So I choose a step size alpha k at every iteration k, and I remove basically a kind of the stochastic version, like basically the sample version of this equation, right, of this quantity. And so what we know is that under appropriate conditions of the alpha k, we can leverage tools from stochastic approximation, like Robbins and Monroe, to show that this thing converges, to the solution, to the v pi, right? As k goes to infinity. Because in a sense, this is an unbiased estimator of basically this thing converges to this thing is an unbiased estimator of the squared Bellman error, right? That's what we think here, right? So in other words, that the thing that I described just so far, you can see it as a stochastic optimization of the squared Bellman error, right? And so I'm just trying to find a zero. I'm trying to minimize the squared Bellman error, and I know that the value function has 0 Bellman error, right? Okay, so and now we are going to try to understand a little bit more how to build from there. And for this, I'm going to just make a simplification that I will assume that the learning rate goes to 0. Like the step size, I'm going to try to make it go to 0. And so, and I will make this small technical assumption that the Markov chain is aperiodic and irreducible, right? This is a relatively mild assumption. And I consider mu to be the stationary distribution. And so as the learning rate goes to 0, if I look at the expected dynamics, like the expected evolution of this temporal difference learning, what I see is that basically the rate of update of the value function at point S is proportional to how often I go to state S. This is the stationary distribution, times basically again the So this is basically just the gradient of the gradient of the square, like it's minus the gradient of the square Bellman error. Okay. So if I write this in a more compact form, basically I write the Bellman equation to be like in linear form, right? This is just a vector of all the value function for all the states, and this is the transition, the Markov transition kernel. I just plug I just isolate the reward and I plug it back here. What you see is the dynamics, the expected dynamics, are modeled by an ODE, which in that case is linear, right? So the ODE in that particular example is driven by this matrix A, and this matrix A is basically completely determined by the environment, right? So at that point, of course, we are not doing any function approximation. We are just we are allowing ourselves to have a different estimate for the value function for every state, right? So the dynamics are driven by this ODE. So what do we know about this ODE? Well, just because we are in this discounted setup, we know that this matrix A is positive definite. I mean, just put it in quote unquote because it's non-symmetric, right? But it's positive definite in the sense that basically the symmetric part is positive definite, right? And as we know, this is sufficient. You know, if I have an ODE where basically the feedback term is positive definite, right? This is sufficient to actually establish convergence, right? Especially even with a linear convergence, with an exponential rate. Of course, as I said, the problem, or like this is actually good to get some intuition, but the problem is that here we are, we are using a different estimate for the value, for the independent estimate for value at each state, right? So basically, we have to keep a big vector of states, and the size of this vector is the size of the state space, right? So this thing will, in general, become very soon very infeasible, right? This is going to blow up for any game that is sufficiently large. And so, if you think about how many states I have in StarCraft, or like how many pixels I have here, or the word configurations, this thing completely blows up, right? So now we have to. So in order to avoid this blow up, as I said, we have to consider this function approximation, right? So now this is we're gonna introduce. We need to modify the dynamics to account for this change of variables, right? This function approximation. So now instead of actually defining the ODE with respect to the value function itself, we need to define the dynamics with respect to the parameters. Right? That's the ones that we are evolving. So this is actually what's done with what is called in the literature the semi-gradient algorithm, like TD0, and we are going to see in a second where does this equation come from, right? So basically, this looks very similar to what we had before, right? This is what we had before. But now we are taking this term and multiplying it by basically the Jacobian of our value function. So is this actually the same? Does it have the same property as before? Is it an stochastic is it an unbiased estimator of the square of the gradient of the square Bellman error? Well, not quite, right? If you look at this object and we look at the gradient of this with respect to theta, right? What we see is that there's a term that is missing. Okay, yeah, here it is. Okay, so if you look at the gradient of the square Bellman error, you see that basically we need to take the gradient of the value function at the current point s, right? But we also would need to take the gradient of the value function at the next point s prime, right? So if you look at this equation, right? If you look at the gradient of this quantity, what you see is that there's a problem, right? Is that if I want to get an estimator for this object, I would need to basically estimate. I would need to have one sample from the future to be able to estimate this point, and another sample from the future to estimate this point, right? And the environment only gives me one sample, right? So this is what's called like a double sample problem, which means that in practice we cannot leverage the nice framework of stochastic optimization. We cannot just say that this algorithm is going to converge, right? Because we cannot create from the environment. We cannot construct an unbiased estimator of the gradient of the square Bellman error. Okay, so in fact we have to settle for something that is not quite a gradient algorithm. It's called a semi-gradient algorithm. Okay, so if we look at the equation that we have in continuous time, that's the equation we have. So this is just the same thing we had before, but now v is itself parameterized by theta, right? So we introduce a new Jacobian term here, right? That's the new thing that we have here. Okay, so what do we know about this ODE? So now in general, this is going to be a nonlinear ODE, right? So what do we know about this about this dynamics? So there are two regimes in which we know something. The first one is when this function approximation is linear, right? So when our mapping from parameters to values is a linear mapping, right? So when this is linear, it's very easy to show that this again is going to be basically this is just going to be a matrix like this object theta, and when we plug it here, what we see is that the ODE with respect to basically the dynamics with respect to the parameters have again the nice property that it's like a linear. The dynamics are still like the ODE is still linear, and the matrix here is again positive definite, right? So we are again in the regime where things converge well. Okay, and this is the result of Titzlikis and Van Roy's, like a very influential result here. Okay, so this like linear function approximation, good. Okay, this is still like a using in a relatively nice environment. Now there's another interesting regime where we know something about this ODE is when the Markov chain is reversible, right? When the dynamics are reversible, what we can show, actually this was shown by this very nice paper by Yann Olivier, is that then in that case our matrix is symmetric, right? And when the matrix is symmetric, the dynamics, actually one can rewrite this term as being the gradient of something, right? And in that case, the gradient here is a Dirichlet energy, right? It's basically the energy of the value function measured with respect to this dot product, right? And so this is, of course, this is only a metric. This is only a dot product when this operator here is symmetric, right? Okay, and so this actually created in the literature the fact that we have no guarantees that this algorithm is going to work for general function approximation. So of course this there are many solutions from there, right? I mean, one thing that people have tried to do in the literature is to say, well, why do we need to settle with this algorithm? Maybe there's a way we can change the algorithm to make it converge. And this is actually something that has also been studied quite a lot in the literature, and people have been developing what's called these 2-time scale algorithms. So I don't know if they are also used in other areas, such as maybe like the other areas of physics and math, but this here is used a lot. And essentially what it means is that you can break the function approximation into one part that looks linear, and one part that looks nonlinear, and you assume that the nonlinear part moves very, very, very slowly with respect to the linear part, right? So you can basically pretend that there's no nonlinearity, right? But what we are going to try to do is to stick with the original simple algorithm and try to see how can we extend essentially these two frameworks. Okay, what can we say beyond these two frameworks? Okay, so can we get consistency in the general case, you might ask? Can we hope to get the general consistency result? Well, the answer is no, right? The convergence is not generic, right? And because we can construct examples where we have divergence, right? And these are very interesting examples. I mean, here, the environment is extremely simple. We have 3 states, right? And you have dynamics that are completely, completely toy. And what we see is that if we had to estimate the value function, right? So this is already with the policy that we have these transitions. So if we could use tabular, so basically if we could represent any function, any value function, we would have the previous ODE, as you see, has the flow lines that correspond to a matrix A that has some curl, right? So basically the matrix A has one component that basically pushes everything to the solution. In that case, I just centered everything to be 0, 0. But because the matrix is not symmetric, it has a curl, like the dynamics basically curl. So if I use a function approximation that is basically chosen almost like adversarially, right? As you can see, the environment is going to push me in that direction, right? But if I wanted to follow a function approximation, I want to find convergence, I should go in that direction, right? So what you see is that the environment is going to push me farther and farther and farther from where I need to be, right? So here I have no problem. I could just follow this flow line, like the trajectory is going to converge. But here I'm basically preventing the model from converging, right? And when you have an environment that would be symmetric, right? The geometric vision is that there's no curl, right? And when there's no curl, things cannot blow up, right? Because the gradient flows, as you know, are stable, right? They dissipate, right? So they are stable. So we shouldn't expect to have a result that establishes convergence all the time. So the question is, what kind of guarantees we can get for nonlinear function approximation? Okay. So we are going to first consider what happens if we just make an assumption that we are going to consider a class of function approximation that are homogeneous of degree h. Right? As a reminder, what is a homogeneous function? Is a function where if I scale the input, I get scale the output, right? And as you know, if I have an activation function that is homogeneous, then I can compose, I can still construct homogeneous functions by composing this activation function with linear maps, right? So this is actually known, it's an elementary computation that this is like that homogeneity is preserved with respect to composition, right? The regular parameters. So what do we know? What happens when our function approximation is homogeneous? Well, so in that case, we get a first certificate that when I use a function approximation that is homogeneous, I cannot have divergence. We cannot have divergence, right? So if I have a function approximation that is homogeneous and a little bit smooth, then the dynamics are essentially trapped into a ball. Like in the limit, my estimator of the value function cannot blow up, right? You might ask, okay, but how does this thing compare or relate to the convergence, right, to the true value function? So the one way to interpret this result is that in the worst case, right, my model is not going to do worse than if I decided to just essentially estimate 0 all the time, right? If I have an algorithm that decides that the value function is 0 everywhere, okay, this estimator is going to be, you agree with me, very bad, but it's not going to diverge, right? So the way you could interpret this result at this point is that, okay, I have a potentially very good estimator, but in the worst case, it's not going to do worse than just doing 0, right? Which might say, okay, this doesn't look very, maybe 0 is really, really bad, and this bound is really, not very useful. So can we have a baseline that is a bit stronger, right? Instead of 0, can we replace the baseline 0 by something that has hope to approximate things a bit better? And maybe you know where I'm going, because now we can just maybe enhance this property with another interesting property that is sorry. It's going too fast. Okay, sorry. Okay, so now I'm going to basically augment my function approximation with one component that is homogeneous as before, but I'm going to plug it into a linear function approximation. Okay, and you might have, this might remind you of these residual networks, right? Residual networks basically take a very simple model, and instead of replacing it by a complicated model, they complement it with a nonlinear model, right? So you are building nonlinearity on top of something that is linear. So what happens in that case? So in that case, essentially the proof goes through, but the only difference is instead of basically have a worst case control with respect to the 0 baseline, now we have a control with respect to the best linear model, right? So in that case, what we show is that in this context, our nonlinear TD dynamics are going to be, in the worst case, they are going to have an error that is of the same order as the error that you would get if you were using linear function approximation. Okay, so this kind of result that says that if I have a nonlinear parameterization and I can certify you that it's going to do no worse than a linear model, this is actually, the results of this flavor also appeared in this nice paper by Ohad Shamir in the context of non-convex optimization, right? So you might argue that these are very weak results, right? I mean, I'm having a nonlinear model, and I'm telling you that if you optimize this linear model, you are going to have an error that is no worse than the linear model, right? Of course, there are many interesting problems. The linear model is going to be very bad, right? But in a sense, that's what it is, right? Non-convex optimization is hard, right? I mean, it's hard to make guarantees that are hard, that go beyond this point. Except, so you might have been following, is that maybe the one way in which I could certify something to have something better than a linear model with a nonlinear model, maybe I can obtain it at the expense of making the model much larger, right? And that's the kind of the other lesson from non-convex optimization, is that in a sense we can compensate for the fact that things are non-convex by having more parameters. So do we have the same phenomenon here? So remember, what we had is that there was this interesting case where if my environment is reversible, then essentially the dynamics become stable, right? Just because they are gradient descent of something. So can we somehow leverage this property? And so let's see very quickly how we can do that. So I'm going to define, how reversible is an environment, right? So if I give you Markov chain, I can assign how reversible it is, like a coefficient, like a scalar coefficient that basically measures the ratio, basically it's like a kind of It's like if you want like a, what's this name? It's a kind of a, like eigenvalue problem, like it's a kind of ratio between the thing here I have basically the symmetric part of the problem, and here I have the anti-symmetric part, right? So basically if the environment was completely reversible, this would be infinite, right? So now what is the statement? Is that if I have a function approximation that is sufficiently well conditioned, in the sense that the condition number of my, basically, so this is also known in the literature now as the neural tangent kernel. So if the condition number of my, basically, function approximation is controlled by this degree of reversibility, then we have global convergence. Okay? So is this property strong? Is it not strong? What does it tell us? So first, is like, there's an interesting link between basically the geometry, like how well my function approximation in this condition versus how curved is my, basically my function, my environment. But of course, what do I need for this condition number to be finite? So in particular, I need to have more parameters than states, right? At this point. So remember that this the V is a mapping that goes from the space of parameters to the space of value functions, right? And the dimensionality of the space of value functions is proportional, is actually the number of states, right? So this mapping in general, this is really something that requires overparameterization, right? Which is not something that I'm sure we have, right? I don't know how many parameters the AlphaGo network had, but I don't know if it's actually of the order of 2 to the 100. I would be surprised, right? So take this kind of result as a kind of a preliminary result, right? We would like, maybe we can think about how to make this result go through with less amount of overparameterization. Okay, so far I basically talked about essentially the weakest possible guarantee of a nonlinear method, right? I'm just interested in understanding, is my algorithm going to converge or not, right? And we have seen is that in the context of reinforcement learning, we are even not at that point, right? So we don't even know the rate of convergence, right? We barely know whether this TD algorithm converges. We are still much farther away in terms of actually the rate of convergence. And another thing that we are not addressing here in this paper, but in this work, but that is, of course, something very, very important, is that I basically just studied the average dynamics, right? Like the expected dynamics. But there's, of course, a very important property for practitioners, that is, what is the sample efficiency, right? How fast do I converge to this expected dynamics in terms of how many interactions do I need to make sure that this is an accurate description. So this is actually an interesting and surprisingly very active and recent area of reinforcement learning, precisely going from these basically non-quantitative statements about consistency to actually quantitative statements that basically control the sample complexity. So as you can see, there's these papers are essentially from the last 2 years, right, where we have done like good progress in the tabular case. Even more recent papers that now jump into the linear function approximation case, and also like a very nice paper by Alec Archibald and colleagues that studies like the third wild category of policy gradient. So with that, I just wanted to, so this is a conclusion. So just to wrap up on what I talked about today, that we just were interested in how bad things can go once you start plugging a nonlinear function approximation into reinforcement learning, right? And what we saw is that there seems to be an interesting interplay between the geometry of your function approximation and basically some properties of the environment, and that we identify that there's this nice, like this homogeneity and this residual aspect that seem to play well. So of course, we are still pretty far from where we want to be. We would like to exploit more regularity, more structure from the environment, right? How can we leverage the fact that some environments might have some, like predictable dynamics or like reward structures that are relatively smooth. And as I said, we really want to understand how to go to sample complexity. So with that, thank you very much. And this is the reference of the paper if you are interested to get the details. Thank you.